Welcome to our presentation in the ASEAN Online Summit 2021. Today we are talking about data-driven risk analysis with Amazon Neptune and the Amazon Elasticsearch service. And we are focusing on the energy industry in our use case. My name is Adrian de Jonge and I'm a partner solution architect at AWS in Singapore. And I am joined on stage by Charles Clusper, who is Director Applied Intelligence at Accenture in Singapore. In this session, you will learn how the energy industry is adopting purpose-built databases. We'll talk about the speed and power of graph databases for highly connected data. And we'll illustrate this with a use case of how graph databases are used for data-driven risk analysis in the energy industry. As part of this use case, we'll explain the difference between basic search and intelligent search and how to achieve intelligent search. And when building a knowledge management solution based on graph databases, natural language processing is a key component. Data is transforming the energy industry. In this slide, you see a visualization of areas in the oil and gas industry where data plays a role. Modernizing the energy industry with data-driven solutions helps make businesses less carbon intensive and accelerates the development of renewable energy businesses. In today's presentation, we will talk about a use case where customers need to do a risk analysis of their equipment as part of acquiring crude oil. And they use a combination of Amazon Neptune and the Amazon Elasticsearch service to power the knowledge management solution that speeds up this risk analysis significantly. Before we dive into this use case, I want to give a bit more generic introduction into graph databases and how they are part of a larger philosophy of purpose-built databases. At Amazon, we recommend customers to use purpose-built databases to optimize the way that they manage and query data. What I mean by purpose-built databases is perhaps best illustrated by looking at common database categories. We see relational databases as one category of purpose-built databases, and this is probably the one that you're most familiar with. Relational databases are here to stay in the purpose-built database philosophy. Just make sure that you use it where it's fit for purpose, and don't use it as a golden hammer. So, if you have a workload where strong consistency matters, you have a clear data schema, but you're not really sure about every single question that will be asked of the data, then relational databases are a good fit. This is where Amazon RDS and Amazon Aurora help you out. Over the years, we have built a number of purpose-built non-relational databases. Perhaps the most well-known is in the category of key value stores with Amazon DynamoDB. This is a database that optimizes running key value pairs with single-digit millisecond latency at a very large scale. A DynamoDB table can have a single item or a trillion items, and it will perform the same. Next is the document category. If you want a flexible way to store and query data using the same JSON document model that you use in your application code, then Amazon DocumentDB is helpful. It is fully managed, compatible with MongoDB, and scales easily to meet customers' growing needs. Suppose you need something even faster than single-digit millisecond latency measured in microseconds. For that, you need an in-memory database, such as Amazon Elasticsearch, which is managed Redis and managed Memcached. Let's say that you have datasets that are really large and have a lot of interconnectedness. For this purpose, we built Amazon Neptune. And we'll talk about this in the remainder of this presentation. But before we get there, let's complete the list. Driven by the rise of IoT devices, IT systems, and smart industrial machines, time series data is one of the fastest growing data types. For this, we have Amazon TimeStream, a purpose-built time series database that became generally available in September 2020. Ledgers are typically used to record a history of economic and financial activity in an organization. For this, it is important to ascertain the integrity of the data, which can be tedious in other databases. To make this easier, we have Amazon Quantum Ledger Database, or QLDB. And this is a fully managed ledger database that provides a transparent, immutable, and cryptographically verifiable transaction log. For applications that require high-speed data processing with single-digit millisecond latency, such as industrial equipment maintenance, a wide column database is a great choice. AWS offers a wide column database with Amazon key spaces for Apache Cassandra. When you use the right tool for the right job, you get the best performance, scalability, and maintainability at the lowest cost. Traditionally, customers have been using relational databases as a single tool for every use case. Because relational databases were not purpose-built for querying and traversing graphs, this leads to a number of problems. SQL, as a query language, is unnatural for querying graphs. It is hard to express your query in SQL, and if you manage to do so, the resulting query is slow due to inefficient graph processing. And the rigid schema is inflexible for changing data. Graph databases are optimized for highly connected data. If we want to use the right tool for the right job, for highly connected data sets, we need a graph database. And on AWS, that means we want Amazon Neptune, which is a fast, reliable, and fully managed graph database. What can you do with the graph database? Let's look at a simple example. Graphs are a data structure. They consist of nodes and links, or vertices and edges if you prefer. And you can then represent relationships between things. And it turns out that graphs show up in all kinds of use cases. For example, social networks, communication networks, network security, they're all well suited. In the illustration, you see a simple graph representing the knowledge we have about Alice and Bob. So when should we use a graph? When you have relationships in your data and you want to ask questions that involve traversing those relationships or expressing patterns over the relationships. Using a graph for these cases is faster, more effective, and easier to operate. Let's look at Amazon Neptune and what it offers in the space of graph databases. Amazon Neptune is delivered as a managed service. And as a managed service, it sits on top of a cloud-native storage layer that is shown in the lower half of the screen. Data is stored in 6 copies across 3 availability zones, and this gives you both high availability and durability of data. The storage layer supports encryption at rest with customer-managed keys in KMS and continuous backups, and the possibility to do cross-region snapshotting. When you write data to the primary node, that data, once committed, is acknowledged by at least 4 of 6 different nodes in the service layer and is then immediately available on the primary node. The read replicas can then read off of the new commit point. Speaking of read replicas, one instance has the role of primary node, and you can then add up to 15 instances that are in the role of read replica. And when you have at least one read replica, you can fail over from the primary node to the read replica in a short amount of time. This is typically done within 30 seconds. In the graph space, there are really 2 major graph models and frameworks. The first is something called a property graph, or sometimes labeled property graph. A property graph consists of nodes and edges, and these nodes and edges can have properties on them. The leading open source framework for property graphs is called Apache Tinkerpop. Tinkerpop works with a graph traversal language called Gremlin. The other framework is called the Resource Descriptor Framework, or RDF. RDF is a recommendation from the World Wide Web Consortium and was originally built to describe resources on the web. RDF expresses graphs in terms of triples, which means a subject, a predicate, and an object. Adrian is a speaker. That would be a triple. And it uses these triples to build up a graph over time. The way that you query an RDF graph is with another World Wide Web Consortium recommendation called Sparkle. Sparkle is a declarative graph query language for RDF. Customers often ask us, which graph model should I use? And from a technical perspective, you could really do any use case with either graph model. What we see is that customers really want both. In some cases, you have data available in RDF that you want to use. In other cases, you have developers who think in terms of nodes and node properties and edge properties, and a property graph is a better fit. You may end up with a combination. Amazon Neptune works really well in combination with the Amazon Elasticsearch service. And vice versa, but that I'll leave for Charles to explain. The Amazon Elasticsearch service is good at managing full text search on your dataset using text indices. You can leverage that capability in your Neptune cluster. With Elasticsearch, you can use fuzzy search, query string, prefix, and some of the other query parameters that Elasticsearch already supports. You can use either a new Elasticsearch cluster and integrate with it, or an existing Elasticsearch cluster and integrate it with Amazon Neptune. You can use a feature in Amazon Neptune called Streams to help synchronize data between Amazon Neptune and the Amazon Elasticsearch service. Now you probably wonder what a query looks like that searches both Amazon Neptune and Elasticsearch. Here's a syntax. On Sparkle, we support the service keyword, which is defined by the standard. But there's an extension on specifying the Elasticsearch endpoint. Similarly, for Gremlin, we have an extension with side effect. And you specify the Elasticsearch endpoint and also the query that you want to run. And here, I would like to hand over to Charles Clousper from Accenture to take us through the use case for Amazon Neptune that he has implemented.
Hi. As Adrian mentioned, this use case focuses on how we have helped our client from the oil and gas industry make better decisions through a better analysis and understanding of the documents and information they had been compiling for years. Those documents could be of various types: historical information of blends purchased, blend analysis performed in the past, industry white papers, professional report, past risk and analysis, and so on. Our clients had basically accumulated years of information that were mostly siloed at different places of the organization: emails, SharePoints, local computer, private notes, and so on. Data were so heterogeneous and so all over the place that it became very hard for our client to retrieve the right information in a timely manner. Our objective was to create for them a platform centralizing all this information to facilitate present and future retrieval. Making the right decision on time would allow our client to buy raw oil at a better price once the due risk analysis performed, increasing significantly its margin by buying unconventional crude cheaper than the most mainstream ones. The last key point on our solution was to implement a scalable and future-proof solution that will grow naturally and support the incremental ingestion of many new data sources in the future. To understand the task at hand, let's look at the high-level platform workflow. We can summarize our workflow as a four-step process. The first step is the platform hydration, where we extract the information from the multiple sources and do a first level of processing, such as document scanning, natural language processing or NLP, and others. The second step is the fact content analysis, where the information extracted from the hydration steps are ingested and merged or combined with existing information. The third step is the search part, where the information is retrieved from the system based on users' queries. by leveraging our knowledge graph and the context map representation that we have created. The fourth step is the feedback part, where the user can rate the result of the system as good or bad. That feedbacks are then collected and will be used later to update the knowledge graph or retraining our models to improve the query matching layer. In terms of architecture, if we have leveraged a traditional data layer composed of an ingestion, an ETL, a data enhancement, and an analytics blocks, and both a knowledge query component and a user interface, the specificity of our system relies on the second layer, the knowledge layer, that we have created specifically for our knowledge representation and management. This layer is composed of the following: the knowledge extraction block, where the raw text is extracted, analyzed, and classified into fact and structured data. The knowledge repository, where the raw data are saved and kept. The relationship and knowledge extraction and indexing, where the facts extracted earlier are analyzed and added to our knowledge graph or knowledge representation. And the knowledge aggregator, where we leverage both our knowledge graph and business representation to extract facts to associate it with the user query and ranked information based on their relevance toward that query. This knowledge aggregator is quite fundamental for infrastructure because, in general, when we talk about information retrieval, different approaches can be considered. The first one, which is kind of a little bit vanilla, look at the user query and search for the presence of certain keywords from this query in the different documents we are searching for. So we are associating terms through the use of word embeddings, for example. The limit of this approach is that it fails to represent the complexity and specificity of a business domain. The second approach, the one we have taken, leveraged the creation of a business-related taxonomy to go from a keyword-based search to a business concept-based search. To summarize, this approach allows us to inject a layer of business understanding to our ingestion and information retrieval. Let's now zoom into how our knowledge management layer works at a high level. As you can see, we still have our different blocks: the ingestion, the knowledge representation, and the retrieval block. The ingestion pipeline enables information to come into the system from all the different sources. Once landed in our system, the knowledge representation process starts, with our Lambda function acting as an orchestrator or coordinator between the different other components. Both Comprehend and SageMaker are used for our natural language processing layer. Comprehend is a dedicated AWS NLP component that provides out-of-the-box models for processes such as name entity recognition or NER, part-of-speech tagging, content identification, topic modeling, and so on. On the other hand, we have SageMaker, which allows us to build custom models that can tackle problems such as document classification, document summarization, fact classification, keyword extraction, etc. Both Comprehend and SageMaker complement each other in our system, classifying the documents by type first, then extracting key facts from each document, doing some topic modeling, and so on, and then looking at the paragraph or sentence level for name entity recognition or part-of-speech tagging. The results from both Comprehend and our models made on SageMaker come back to the Lambda, which then stores the detected fact to the knowledge graph. To avoid losing any information, in particular relationship or nodes that may be missing in the knowledge graph, we also use AWS Elasticsearch as a backup, or more precisely, as a way to still perform free-form queries. To retrieve information, the user query is analyzed by the Lambda on the right side of the screen. The related information is retrieved in the knowledge graph and the Elasticsearch instance, and those information are ranked based on their estimated relevance. A sorted list of information is sent back to the UI to be displayed to the user. Here is an example on how the information will be treated. As you can see in this example, an unstructured file arrives to our system. It could be coming from all the different sources we are accepting. We are treating here a specific piece of information regarding a type of crude, here champion, which has a low basic nitrogen and other informations. Our first step, once the information is extracted from the document, is to contextualize the information using our business representation or our taxonomy. Here, a new paragraph. It enables us to detect the different parts and entity composing our paragraph and structure the information to our knowledge graph. In this example, we are recognizing an entity or a CRUD of type champion and detect a relationship between this entity and another entity, here of type low basic nitrogen. This relationship is classified as type is characterized by, and so on and so forth, iteratively allowing the knowledge graph to grow through times through the detection of new facts. Another important consideration is that when ingesting new data to a knowledge graph, we are able to look into it to search if any similar entity already exists and the type of relationship and properties the existing entity has and the new one have also in common. If we detect similarities between those entities, we can potentially associate the relationship from one of the entity to the other. For example, if I have a crude A, which has certain list of properties, such as a certain level of basic nitrogen and a sulfur, and then I ingest later on a new crude B, which has a similar basic nitrogen and sulfur levels, but have also information about the risk associated to it due to some feedback from an agent who tried maybe to process it on the field, I can estimate that there is a probability that the crude A also has a similar risk as the crude B. This makes the whole structure extremely dynamic and enable the graph to grow automatically. Of course, sometimes new information or contradictory information can appear, creating conflict during the ingestion. Handling such cases can be done in different ways. First, by looking at the timestamp of each information, which allows us to update the list of facts in our knowledge graph by the most recent one, for example. Second, by looking at the existing fact and how a new fact can alter an existing property or relationship, and then updating or creating a new relationship between nodes. Third, by calculating some score or some sort of reliability score for the different sources providing information to rank the fact based on who has provided them. Or finally, by enabling also the user to give direct feedbacks through the UI, a thumbs up, a thumbs down, or a ranking of the information. To conclude, I'd like to mention that there are many other challenges that we haven't had the time to mention here that we have to consider when building such a system. For example, the user's query analysis, which is when the user enters a query, we need to expand each query to associate additional attached concept to it to make sure each query is well understood, contextualized, and user receives the right information at the end. This is what we call the query expansion, where we look at the different terms used in the question and try to understand both the synonymy, which are different words that have the same meaning, and the polysemy, which is different meanings from the same word. For each term, we're trying to analyze that. And then weight those information to the context of the questions. Other than that, some of the key takeaways from the work we have done are: when implementing search capabilities, if applied to a specific business domain, vanilla text search may not be good enough to recognize and extract key business information from vast amounts of unstructured and structured data. Knowledge graphs are a great way to handle this domain specificity by both helping the information extraction during the ingestion phase, but also helping contextualizing query during the retrieval phase. There are many ways to move forward and improve the result of our platform. One, for example, would be to get more annotated data to use to train our classification model. Another way would be to improve the ranking mechanisms. Another better way could be to vectorize user query to enhance the fact association to it. Possibilities are multiples.
Thank you, Charles. So to summarize, we started explaining why you should use purpose-built databases for the best result. We looked into detail at how graph databases are powerful for highly connected data, how a graph database applies to unstructured information processing, and how a graph database, combined with Elasticsearch, facilitates intelligent search. And Charles showed how natural language processing is a key component of knowledge management. So in short, I'd encourage you, use graph databases with Amazon Neptune, supported by the Amazon Elasticsearch service for your use cases with highly connected data. To further your cloud journey, you can take a look at our training and certification resources to get digital training, classroom training, and more. Thank you for attending this session. This was Charles Clousper from Accenture and Adrian de Jonge from AWS Singapore. Please submit the survey to help us gear up for an improved summit experience for you in future. If you have any questions, do feel free to ask them in the Q&A chat window as well.